Good day, everyone. This is the IMWUT group from Xi'an Jiaotong University. We are here to present the project titled XRF55, a radio frequency dataset for human indoor action analysis. This project was led by Fei Wang in collaboration with Yizhe Zhu, Mengdie Zhu, Han Ding, and Jingsong Han. The main contribution is the development of a novel radio frequency dataset specifically designed for analyzing human indoor actions. RF devices, like Wi-Fi adapters, are commonly found in our everyday environments, making them a convenient and accessible tool for indoor action monitoring. Unlike cameras, RF-based solutions raise fewer privacy concerns, as they do not capture identifiable images, and they are also robust to environmental factors such as lighting and occlusions. These attributes make RF-based methods promising for applications in elderly care, health monitoring, smart home systems, and security surveillance. However, despite their potential, most current RF action analysis efforts remain in the proof-of-concept stage, and large-scale real-world deployments are still limited. In AI, we've seen the transformative power of scaling laws, as evidenced by models like Vision Transformers trained on 300 million images, CLIP with 400 million text-image pairs, and the Segment Anything model, SAM, trained on 11 million images and 1 billion masks. Similarly, large language models, such as Llama, have been trained on trillions of tokens. For video-based action recognition, the large-scale Kinetics 400 dataset has enabled even basic models like ResNet 3D, which simply extends 2D convolutions to 3D, to outperform more complex, custom-built approaches. This demonstrates that scaling can significantly improve model performance. Similarly, by scaling RF datasets, we could address challenges in real-world deployments, such as handling new users in unfamiliar environments, performing novel actions in varied poses or orientations. This would bring us closer to achieving true zero-shot performance in real-world settings, where models can generalize to entirely new scenarios without additional training. In the RF sensing community, datasets like YAR, IMWUT, WITER3 are much smaller. In contrast, early video datasets in the AI community, such as UCF101 and HMDB51, already featured hundreds of classes and tens of thousands of samples. Even more striking is the size of recent video datasets like Kinetics 400 from DeepMind, with 400 classes and 160,000 samples, or Google's Something Something V2, which has 174 classes and over 220,000 samples. This comparison underscores the need for larger RF datasets to parallel the successes seen in video-based action recognition and help RF-based models reach their full potential. To scale up RF datasets effectively, there are several key questions we need to address. First, which types of actions should we focus on? Since most potential use cases for RF-based action recognition are indoors, indoor actions are our primary target. We can draw inspiration from existing video datasets to categorize actions. For instance, UCF101 includes categories like human-object interaction, body motion only, and human-human interaction. Similarly, HMDB51 and Kinetics 400 classify actions into person-object interactions, singular person actions, and person-person interactions. The next step is selecting specific actions. We can either pull from video datasets to add more action classes or reference actions from existing RF papers that align with common RF sensing applications. Finally, we need to consider which RF technology to use. The most widely used modalities include RFID for decimeter wave sensing, Wi-Fi for centimeter wave sensing, and millimeter wave radar for even finer resolution. In this project, we have referred to a wide range of both video action datasets and RF sensing papers. From the video domain, we analyzed 16 key datasets, including well-known examples like Kinetics, UCF101, HMDB51, and Something Something, among others. In addition, we studied 19 RF sensing papers such as YAR, WITER 3.0, NTU-Phi, RF Finger, and EIs. By leveraging the knowledge from both AI and RF communities, we aim to design a comprehensive and scalable RF dataset that can handle a wide range of actions and real-world challenges. The XRF55 dataset has 5 action categories, a total of 55 action classes. 15 human-object interaction actions. including whole home daily actions, actions in kitchen, in bathroom, and healthcare actions such as drinking, eating, and smoking. 7 human-human interaction actions, including social actions, shaking hands, hugging, and violence actions for applications of domestic violence and invasion detection. 8 fitness actions, with equipment such as hula hooping, and actions without equipment, such as tai chi and high leg lifting. 14 body motion actions, including whole home daily actions, healthcare actions such as falling on the floor, stretching, patting on the shoulder, and playing musical instruments, such as playing erhu, drum, and ukulele. 11 human-computer interaction actions, hand gestures such as push and pull, and interaction actions for situations when hands are not free, such as foot stamping, shaking head, and nodding. The diversity of actions represented in the XRF55 dataset makes it a valuable resource for various applications, including smart home technology, healthcare monitoring, and security systems. The XRF55 dataset incorporates 3 RF modalities alongside paired RGB DIR video clips. The timeline for the dataset's collection spans nearly a year. The dataset utilizes various technologies including 23 RFID tags, 9 Wi-Fi, 1 mm wave radar functioning in the 60 to 64 GHz range, 1 Azure Connect, which captures RGB, depth, and infrared data. The combination of these modalities enriches the dataset, providing a comprehensive basis for action recognition and analysis in indoor environments. The XRF55 dataset comprises a total of 39 subjects engaging in 4 different scenes, covering 55 distinct action classes, with each action being repeated 20 times. This leads to an impressive total of 42,900 samples, amounting to over 59 hours of effective action duration. Compared to existing open-sourced or non-open-sourced RF work, XRF55 has good advantages in the number of action classes, number of samples, duration, and diversity of sensing modalities. In terms of data volume, the raw RF data collected amounts to 3 terabytes, and after preprocessing, it is reduced to 180 gigabytes, making it more manageable for researchers. Importantly, all components of the XRF55 dataset are open-sourced, ensuring accessibility for researchers and developers in the community. The XRF55 dataset supports research on RF modality collaboration. Motivation: as the number of RF devices increases in indoor environments, it becomes crucial to explore how these multiple modal RF devices can effectively operate together. Purpose: the goal of this research is to enable each device or modality to function independently, ensuring that even if some devices are inaccessible or non-operational. This framework is distinct from traditional teacher-student models and modality fusion approaches. The framework utilizes KL divergence losses to facilitate knowledge transfer among modalities, allowing them to benefit from shared information while maintaining their unique operational capabilities. Once the learning process is complete, each modality can operate independently without relying on the others, making the system more resilient and flexible. Modality collaboration plays a significant role in enhancing action recognition performance across different RF modalities. RFID performance: the action recognition accuracy for RFID improved from 59.22% to 64.78%, demonstrating a notable enhancement due to collaborative learning. We also see enhancement in Wi-Fi and wave radar performance. XRF55 supports some other research. For example, one follow-up work, RF Clip, is inspired by the architecture and methodologies of existing models like Clip, Video Clip, and Audio Clip. Here are the main components of the RF Clip framework. First, the XRF55 dataset provides a unique advantage as it contains paired action labels, videos, and RF data. Second, the action labels are fed into a frozen text head, which can operate with or without prompt engineering. For instance, using a prompt like an action of. Third, the video data is input into a frozen image head, typically utilizing a pre-trained model like Video Clip. This enables the model to extract features from the visual domain without requiring extensive retraining. Fourth, the RF data serves as input to the audio head, which undergoes fine-tuning, such as LoRa and adapter. Overall, this work aims to leverage multimodal learning for zero-shot action recognition, potentially enabling applications across diverse environments without requiring extensive retraining on new actions. Another follow-up work focuses on the concept of RF class incremental learning, which is essential for adapting to the evolving needs of users. The motivation is, in the future, there will be RF sensing service providers to provide models to users. Purpose: the primary goal is to provide updated models that support customized functionalities for diverse user needs. This customization can enhance user experience and increase the practicality of RF sensing applications. Class incremental learning allows models to learn from new classes of data while retaining knowledge from previously learned classes, making the system more versatile and responsive. The XRF55 dataset contains 55 action classes. Initially, a subset of actions will be used to train a base model. This base model will serve as the foundational service offering for users. As new actions are introduced, the model can be continuously updated to incorporate these new classes. This ensures that users have access to the most relevant and current models tailored to their unique requirements. By employing RF class incremental learning, we can create a responsive and user-centric RF sensing ecosystem that evolves alongside the needs of its users, promoting enhanced usability and adaptability in various applications. Another follow-up work focuses on RF dataset distillation, a critical strategy for managing the challenges posed by large volumes of RF sensing data. Motivation: as RF sensing technology progresses, we anticipate the generation of vast amounts of RF data. This increase in data volume can present storage challenges and slow down model training processes. Purpose: the main goal of dataset distillation is to reduce the storage requirements of large datasets while simultaneously speeding up the model training process. The XRF55 dataset contains 420 training samples for each action, providing a substantial amount of data for effective training. By employing dataset distillation techniques, we can reduce the XRF55 dataset to 1 or 10 samples for each action. A model will be trained using the distilled version of XRF55. The aim is to achieve comparable action recognition accuracy to that of the model trained with the full XRF55 dataset. Our latest published work, which focuses on multi-person 3D pose estimation using RF signals. The work is titled Person in Wi-Fi 3D, End-to-End Multi-Person 3D Pose Estimation with Wi-Fi, which has been accepted for presentation at CVPR 2024. Objective: this research addresses the challenge of estimating the 3D pose of multiple individuals in real time using Wi-Fi signals. It presents a novel approach to capture human movement and posture without the need for traditional visual sensors. In this concluding slide, we highlight our vision for the XRF55 dataset to support ongoing research in the field of RF sensing and action recognition. We welcome researchers to explore and utilize the XRF55 dataset. Access can be gained through our webpage. In the project website, we share: first, source code; second, all dataset, including videos; third, tutorial for hardware setup including Wi-Fi, RFID, wave radar, Connect; fourth, tutorial to use XRF55; fifth, Q&A on XRF55. By providing these resources, we hope to inspire further innovation and research collaborations in the area of RF sensing and action analysis. We welcome questions and discussion. Together, we can drive innovation in RF sensing and action analysis. We look forward to feedbacks and collaboration. Thank you for your attention.